The universe has a way of making us feel small, but tonight I want you to sit with a feeling that goes beyond small, beyond insignificant, into a territory where human language starts to break down entirely. Imagine, if you can, standing at the edge of everything you have ever known. Not the edge of your city, not the edge of your country, not even the edge of your planet, but the edge of a structure so monumentally vast that the very concept of edges becomes almost meaningless. For centuries, astronomers have been trying to answer what seems like a simple question. How big is the Milky Way? How large is this swirling collection of stars that we call home? It sounds straightforward, doesn't it? Measure the distance from one side to the other, write down the number, and move on. But the universe doesn't give up its secrets that easily. And every time we thought we had the answer, every time we printed a number in our textbooks and taught it to our children, the galaxy revealed itself to be larger, more complex, more bewildering than we had imagined. And now, finally, after decades of technological advancement, after missions that have mapped billions of stars with precision our ancestors couldn't have dreamed of, we have an answer. But here's what keeps astronomers awake at night, what makes this discovery so profound. The Milky Way isn't just a little bigger than we thought. It isn't 10% larger or even 50% larger. The true size of our galaxy stretches so far beyond the old estimates that we have to fundamentally reconsider what we mean when we talk about our cosmic home. The numbers are so large that they stop functioning as numbers in any meaningful sense and start functioning as poetry, as attempts to gesture towards something that lies beyond the reach of human intuition. Welcome back to Sleep Time Science, your companion for those quiet hours when the world has gone still, but your mind refuses to follow. If you're new to this channel, this is a place where we explore the deepest questions of existence in a way that's designed to comfort and fascinate, to give your wandering thoughts somewhere beautiful to land as you drift toward sleep. We take the mysteries that have puzzled humanity for generations, and we sit with them, turn them over, examine them from angles you might not have considered before. There's no rush here, no pressure, at just the gentle unfolding of knowledge about the cosmos we inhabit. If you find yourself enjoying this journey tonight, if the vastness of the galaxy brings you some strange form of peace, I would be grateful if you would consider subscribing to the channel and perhaps hitting that notification bell so you don't miss our future explorations. And for those of you who have been here before, who have traveled with me through black holes and quantum mysteries and the lives of dying stars, thank you. Thank you for coming back, for making this community what it is, for sharing your curiosity with me. Tonight's journey is going to be a long one, so settle into your pillows, let your body relax into whatever surface is supporting you, and prepare to have your sense of scale permanently altered. Let me begin by painting a picture of what most of us learned about the Milky Way, the comfortable image that has been passed down through generations of astronomy, textbooks, and planetarium shows and educational documentaries. You've probably heard the number before, 100,000 light years. That's how wide our galaxy supposedly spans. A flat disk of stars stretching 100,000 light years from edge to edge, with our solar system tucked away about 26,000 light years from the center. It's a tidy number, easy to remember, impressive enough to generate a sense of awe, but small enough to fit neatly into our mental model of the universe. 100,000 light years. We printed it on posters, we taught it in schools, we built our understanding of galactic structure around it. But here's something that doesn't get mentioned often enough. That number was always an approximation, always a best guess based on limited data, always subject to revision as our instruments improved and our techniques became more sophisticated. Science doesn't work by discovering perfect truths and carving them in stone. Science works by building progressively better models, by constantly questioning what we think we know, by remaining humble in the face of a universe that is always more complicated than our theories suggest. And the story of the Milky Way's size is a perfect illustration of this process. A tale of continuous revision that stretches back centuries and continues to this very day. To understand why measuring our galaxy is so difficult, you need to appreciate a fundamental problem that has plagued astronomers since the beginning. We are inside the thing we are trying to measure. Imagine being an ant trying to determine the size of the forest you live in without ever being able to leave the forest, without being able to fly above the canopy and look down at the whole thing at once. All you can see are the trees immediately around you, and from those trees you have to somehow deduce the extent of the entire forest in every direction. This is precisely the challenge facing astronomers. We cannot step outside the Milky Way and photograph it from a distance. We cannot travel to another galaxy and look back at our own. We are embedded within the structure, surrounded by it in every direction. And everything we know about its size and shape has to be inferred from the limited view we have from our single vantage point. One small planet orbiting one ordinary star in one unremarkable corner of the galactic disk. Every measurement is indirect. Every conclusion is built on chains of inference that stretch back through layers of assumption and approximation. The journey to understand our galaxy's true dimensions begins in the ancient world, with people who looked up at the night sky and noticed something strange. There was a band of pale light stretching across the darkness, a ghostly river that appeared every clear night and seemed to encircle the entire sky. Different cultures gave it different names and different meanings. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, which eventually gave us our word, galaxy. And they saw it as the milk of the goddess Hera, sprayed across the heavens when the infant Hercules was pulled away from her breast. The Romans called it the Via Lactea, the road of milk, a celestial pathway traveled by the gods. Other cultures saw a river of souls, a backbone of the night, a path leading to the afterlife. But whatever meaning people assigned to it, the fundamental question remained unanswered. What was this thing? What was the Milky Way actually made of? The philosopher Democritus, living in ancient Greece around 400 years before the Common Era, made a guess that was remarkably prescient. He suggested that the Milky Band might be composed of countless distant stars, so numerous and so faint that the human eye could not distinguish them individually, but could only perceive their combined light as a pale glow. It was a beautiful intuition, a leap of reasoning that would not be confirmed for more than 2,000 years. But it was also just a guess, one philosophical speculation among many, lacking the tools to distinguish it from the countless other theories that ancient thinkers proposed. The first genuine breakthrough came in 1610, when a man named Galileo Galilei pointed a new invention called a telescope at the Milky Way, and saw something that changed our understanding forever. The pale glow resolved into stars. Countless individual points of light appeared where before there had been only a diffuse shimmer. Democritus had been right. The Milky Way was not a river or a road or the milk of a goddess. It was an incomprehensibly vast collection of stars, so distant and so numerous that the unaided eye blended their light together into that familiar band across the sky. But this discovery, revolutionary as it was, immediately raised new questions that Galileo could not answer. How far away were these stars? How many of them were there? What shape did they form in space? The telescope had revealed that the Milky Way was made of stars, but it had said nothing about the scale of the structure. The stars could have been relatively close and relatively few, or they could have been unimaginably distant and unimaginably numerous. Galileo had no way to tell the difference. For more than a century after Galileo, astronomers struggled with the problem of cosmic distances. The stars seemed impossibly remote, so far away that they showed no apparent motion even when observed from opposite sides of Earth's orbit around the Sun. This lack of detectable parallax, the apparent shift in position that should occur when you view an object from different angles, set a lower limit on stellar distances, but couldn't determine what those distances actually were. It was like knowing that a mountain was at least 10 miles away because you couldn't see it getting any closer as you walked, but having no way to determine whether it was 20 miles away or 200 miles away or 2,000 miles away. The stars kept their secrets, twinkling in apparent stillness, revealing nothing about the true scale of the galaxy they inhabited. Then, in the late 1700s, a remarkable figure entered the story. William Herschel was a German-born musician who had immigrated to England and developed an obsession with astronomy. He built his own telescopes, grinding mirrors by hand to create instruments more powerful than anything available at the time. And he set himself an audacious task. He would count the stars. He would systematically survey the entire sky, recording how many stars appeared in different directions, and from this data, he would deduce the shape and size of the stellar system we inhabit. Herschel's approach was clever, even if his conclusions were flawed. He assumed that his telescopes could see to the edge of the stellar system in every direction, that the darkness beyond the faintest visible stars represented genuine emptiness rather than simply the limits of his instruments. And based on the number of stars visible in different directions, he concluded that we lived within a vast lens-shaped collection of stars, flattened like a disk, and stretching much further in the plane of the Milky Way than perpendicular to it. His model placed our solar system near the center of this disk, a position of apparent privilege that would later turn out to be completely wrong. And his estimate of the disk's size was wildly inaccurate. He guessed it was perhaps 8,000 light years across, a number we now know to be off by more than a factor of 10. But despite these errors, Herschel had accomplished something revolutionary. He had attempted to measure the unmeasurable, to put numbers to a structure that previous generations had merely gazed at in wonder. He had treated the galaxy as a physical object with definite dimensions, rather than simply a beautiful feature of the night sky. The 19th century brought gradual progress, but no dramatic breakthroughs. Astronomers refined their techniques, developed better instruments, discovered new types of stars and nebulae. They mapped the Milky Way in increasing detail, tracing the band of light across the sky and noting the distribution of star clusters and fuzzy patches that might be distant clouds of stars, or something else entirely. But the fundamental problem remained. Without accurate distances to stars, without some way to measure how far away these points of light actually were, any estimate of the galaxy's size was little more than educated guesswork. The universe remained frustratingly out of reach, as its true scale hidden behind a veil of apparent proximity. Stars looked close because they were bright, or they looked distant because they were faint. But there was no reliable way to distinguish between a nearby dim star and a faraway brilliant one. The cosmos kept its measurements to itself. The breakthrough finally came in the early 20th century, and it came from an unexpected source. Henrietta Swan Leavitt was one of the women employed at Harvard College Observatory as a human computer, a worker hired to perform the tedious calculations and classifications that male astronomers considered beneath their dignity. The women were paid poorly, given no recognition, and forbidden from using the observatory's telescopes. They were expected to be invisible, interchangeable cogs in the machinery of astronomical research. But Henrietta Leavitt had a sharp mind and a careful eye, and she noticed something that would revolutionize our understanding of the universe. She was studying a type of star called a Cepheid variable, stars whose brightness fluctuates in regular cycles, growing brighter and dimmer over periods of days or weeks. These stars had been known for some time, but no one had thought much about them until Leavitt began examining Cepheids in the small Magellanic Cloud, a fuzzy patch in the southern sky that we now know is a small galaxy orbiting our own. Because all the stars in the Magellanic Cloud are at roughly the same distance from Earth, Leavitt could compare their apparent brightnesses without worrying about the confounding effects of distance. And she discovered something remarkable. The Cepheid variables in the cloud showed a tight relationship between their brightness and their period of fluctuation. Brighter Cepheids took longer to complete their cycles. Dimmer ones pulsed more quickly. This period luminosity relationship, as it came to be called, was the key to measuring cosmic distances. If you knew how long a Cepheid took to fluctuate, you could determine its true brightness. And if you knew its true brightness, you could compare it to how bright it appeared in your telescope and calculate how far away it must be for that much dimming to occur. Henrietta Leavitt had handed astronomers a cosmic measuring tape, a way to determine distances across spans so vast that no previous method could touch them. The universe was suddenly measurable in ways it had never been before. And the first person to fully exploit this new tool was Harlow Shapley, a young astronomer working at Mount Wilson Observatory in California. Shapley turned his attention to the globular clusters, ancient spherical collections of hundreds of thousands of stars that orbit the Milky Way like bees around a hive. By finding Cepheid variables within these clusters and measuring their periods, he could calculate how far away each cluster was. And what he found was disturbing. The globular clusters were not distributed evenly around us. They clustered heavily toward one region of the sky, in the direction of the constellation Sagittarius. Shapley realized what this meant. We were not at the center of the galaxy. The Sun and Earth were located far from the middle of the stellar system, out in what might be called the galactic suburbs. As the true center of the Milky Way lay in the direction of Sagittarius, perhaps 25,000 to 30,000 light years away. It was another Copernican revolution, another dethronement of humanity from a position of cosmic privilege. First, we learned we weren't at the center of the solar system. Now we learned we weren't at the center of the galaxy either. Shapley's measurements also revised our understanding of the galaxy's size. He estimated the Milky Way was about 300,000 light years across, far larger than Herschel had imagined. This number would later be revised downward, but the direction was clear. The galaxy was bigger than anyone had suspected. And there was another question looming on the horizon, a debate that would shake the foundations of astronomy. Scattered across the sky were fuzzy patches called spiral nebulae, some of them showing elegant pinwheel structures when photographed through large telescopes. Were these nebulae part of our Milky Way, or were they separate systems entirely, island universes unto themselves? This became known as the Great Debate, a genuine scientific controversy that split the astronomical community in the 1910s and 20s. On one side were those who believed the Milky Way was essentially the entire universe, with the spiral nebulae being relatively nearby objects within it. On the other side were those who believed the universe extended far beyond our galaxy, with the spiral nebulae being distant galaxies, comparable in size to our own. The implications were staggering. If the spiral nebulae were inside the Milky Way, as the universe was enormous but comprehensible. If they were outside, the universe was vastly larger than anyone had dared to imagine. The debate was settled in 1924 by Edwin Hubble, who used the new 100-inch telescope at Mount Wilson to observe individual Cepheid variables in the Andromeda Nebula. Applying Leavitt's period luminosity relationship, he calculated that Andromeda was approximately 900,000 light years away, far too distant to be part of our galaxy. The Andromeda Nebula was not a nebula at all. It was the Andromeda Galaxy, a separate island universe containing its own billions of stars. And if Andromeda was a galaxy, then so were the other spiral nebula scattered across the sky. The universe had suddenly expanded beyond all previous imagination. Our Milky Way was not everything. It was just one galaxy among what would eventually turn out to be hundreds of billions. The cosmic ocean was vaster than any explorer had dreamed. Through the middle decades of the 20th century, the picture of the Milky Way gradually came into focus. Radio astronomy allowed astronomers to peer through the clouds of dust that blocked visible light, revealing the galaxy's spiral structure for the first time. Infrared observations detected the heat from stars hidden behind those same dust clouds. By the 1990s, the consensus estimate had settled on a comfortable number. The Milky Way was about 100,000 light years in diameter, with the Sun located roughly 26,000 light years from the center. This became the textbook figure, the number repeated in countless documentaries and museum exhibits. 100,000 light years, large enough to inspire awe, small enough to fit in our heads. A comfortable measurement for a cosmic home. But even as this number became canonical, astronomers suspected it was incomplete. The edges of the galaxy were poorly mapped, the faint outer stars difficult to detect against the background glow of more distant galaxies. The dark matter that appeared to surround every galaxy implied a structure extending far beyond the visible stars. And the techniques available, while sophisticated by historical standards, were still limited in their precision. The true size of the Milky Way remained uncertain, waiting for better instruments, better methods, better data. That better data would come in the 21st century from a spacecraft designed specifically to map our galaxy in unprecedented detail. And what it revealed would force us to redraw our mental image of our cosmic home once again. The story of measuring our galaxy is fundamentally a story about human ingenuity confronting the impossible, about minds evolved on African savannas, somehow developing the tools to comprehend structures that span hundreds of thousands of light years. To truly appreciate what we have discovered about the Milky Way's size, we must first understand the revolutionary technologies that made these discoveries possible. Because without these instruments, we would still be guessing, still be staring at that pale band of light across the sky and wondering about its true extent. The most transformative of these technologies arrived in December of 2013, when the European Space Agency launched a spacecraft called Gaia from French Guiana into an orbit around the Sun. Gaia is not a telescope in the traditional sense. It does not take beautiful photographs of nebulae or peer into the hearts of distant galaxies. Instead, it does something far more fundamental and far more revolutionary. It measures positions. It measures the precise locations of stars with an accuracy that previous generations of astronomers could not have imagined possible. To understand how precise Gaia is, consider this comparison. Gaia can measure the position of a star with the same accuracy as measuring the width of a human hair from a distance of 1,000 kilometers. It can detect the apparent motion of stars so subtle that it would take centuries for the movement to become visible to less sophisticated instruments. This extraordinary precision allows Gaia to do something that transforms our understanding of the galaxy. It can measure parallax, that tiny apparent shift in a star's position that occurs as Earth orbits the Sun, for stars that are incredibly far away. And from parallax, we can calculate distance with genuine reliability, not estimates or approximations, but actual measurements grounded in geometry and the known size of Earth's orbit. By its latest data release, Gaia had cataloged nearly 2 billion stars, measuring their positions, their distances, their velocities through space, their colors and temperatures and chemical compositions. This is not just an incremental improvement over previous surveys. This is a transformation in kind and a leap from sketching the outlines of a continent to mapping every road and river and mountain within it. For the first time in human history, we have a genuine three-dimensional map of the Milky Way, not an artist's impression or a theoretical model, but an actual representation built from measurements of individual stars. And this map has revealed that everything we thought we knew about our galaxy size was incomplete. The disk of the Milky Way, that flat spiral of stars and gas and dust that constitutes the most visible part of our galaxy, turns out to be significantly larger than the 100,000 light years we had long believed. Studies combining Gaia data with other surveys have pushed this number to at least 170,000 light years, and some analyses suggest it may extend to 200,000 light years or more. This is not a minor correction. This is nearly doubling the diameter of the structure we call home. The stars that trace the outer edges of this disk are faint and scattered, difficult to distinguish from the background of more distant galaxies. But they are there, gravitationally bound to the Milky Way, participating in the grand rotation around the galactic center. But Gaia is only part of the story. While optical telescopes like Gaia map the stars we can see, radio telescopes probe regions that visible light cannot reach. The Milky Way is filled with dust, tiny particles of carbon and silicon and ice that absorb and scatter starlight, hiding vast regions of the galaxy from our optical view. And this dust is why the band of the Milky Way appears patchy and mottled rather than uniform, why there are dark lanes threading through the bright glow. Radio waves pass through this dust as if it were not there, allowing astronomers to detect signals from the farthest reaches of the galaxy. Hydrogen, the most abundant element in the universe, emits radio waves at a characteristic wavelength of 21 centimeters. And by mapping this emission, radio astronomers have traced the structure of the galaxy far beyond what optical observations alone could reveal. Arrays of radio telescopes, working together as if they were a single instrument spanning continents, have detected hydrogen gas and faint stellar signals at distances that extend the known galaxy far beyond its visible disk. Perhaps most remarkably, the astronomers have discovered what might be called galactic archaeology, a way of reading the history of the Milky Way written in the motions of its stars. Scattered throughout the galaxy are stellar streams, long ribbons of stars that share common velocities and common origins. These streams are the remnants of smaller galaxies and star clusters that the Milky Way has consumed over billions of years, torn apart by gravitational forces and stretched into elongated structures that wrap around the galaxy like threads around a spool. By mapping these streams, astronomers can work backward to understand the gravitational field that shaped them. And from that gravitational field, they can deduce the total mass and extent of the Milky Way, including the dark matter that produces gravity but emits no light. These streams extend to enormous distances from the galactic center, hundreds of thousands of light years out into the darkness. And their very existence tells us that the Milky Way's gravitational influence, and therefore its true size, reaches far beyond what any simple measurement of visible stars would suggest. The galaxy is not just what we can see. It is an enormous gravitational structure that shapes the motions of objects across vast reaches of space, a structure whose true boundaries lie in the distant darkness where the last faint stars still feel the pull of home. The numbers that have emerged from these modern measurements force us to reconsider what we mean when we talk about the size of a galaxy. There is no hard edge, no cosmic fence marking where the Milky Way ends and intergalactic space begins. Instead, the galaxy fades gradually, stars becoming sparser and sparser, until eventually there are no more stars at all, just the invisible dark matter continuing outward into the void. So astronomers have developed different definitions of size, different ways of drawing boundaries around a structure that has no natural boundary. There is the visible disk, the spiral arms and the spaces between them, the region where most of the galaxy's stars and gas reside. This disk, we now know, extends at least 170,000 to 200,000 light years in diameter, nearly twice the old textbook figure. But the disk is not flat and uniform at its edges. It warps and ripples, probably due to gravitational interactions with satellite galaxies that orbit the Milky Way like moons around a planet, the Large Magellanic Cloud. And visible from the southern hemisphere as a fuzzy patch of light, is massive enough to tug on our galaxy's disk and bend it out of shape. These warps and ripples extend the effective size of the disk even further, creating a structure that is more complex and more extensive than the simple flat spiral we often imagine. Beyond the disk lies the stellar halo, a vast spherical region populated by ancient stars and globular clusters, the oldest objects in the galaxy. These halo stars are not numerous compared to the disk, but they extend to enormous distances. Recent surveys have detected stars that appear to be gravitationally bound to the Milky Way at distances of 300,000 light years from the center, and some studies have found potential member stars even further out, and at 400,000 or 500,000 light years. At these distances, our nearest major galactic neighbor, the Andromeda galaxy, is only about 5 times further away. The stellar halos of the Milky Way and Andromeda may already be touching, their outermost stars mingling in the vast darkness between the two galaxies like the intertwined fingers of reaching hands. This halo is not uniformly distributed. It contains substructures, the remnants of those consumed dwarf galaxies, clumps and streams of stars that retain the memory of their origins even as they are gradually mixed into the larger population. The halo is a graveyard and a museum, a record of billions of years of galactic history written in the positions and motions of ancient stars. But even the stellar halo does not represent the true extent of the Milky Way. Surrounding everything, both disk and halo, is the dark matter halo, an invisible envelope of matter that we can detect only through its gravitational effects. This dark matter constitutes roughly 85% of the galaxy's total mass. Without it, the stars in the outer regions of the disk would be moving too fast to remain bound to the galaxy. They would fly off into intergalactic space like water droplets from a spinning wheel. The fact that they don't, the fact that stars at the edge of the visible galaxy orbit at velocities that imply far more gravitational pull than the visible matter can provide, tells us that something invisible is holding everything together. Studies of satellite galaxy motions, of stellar stream trajectories, of the subtle bending of light from more distant objects, all converge on the same conclusion. That the Milky Way's dark matter halo has a radius of approximately 600,000 to 1 million light years. This means the total extent of the galaxy, including its dark matter envelope, could be nearly 2 million light years in diameter. The beautiful spiral we photograph, the glowing band across the night sky, is just the bright center of an enormous invisible structure, like the glowing filament inside a light bulb surrounded by the much larger glass envelope. These numbers we have been discussing, these measurements of hundreds of thousands and millions of light years, exist in a realm so far beyond human experience that they risk becoming meaningless. Mere sounds we make with our mouths or symbols we write on pages without any genuine comprehension behind them. And a light year is approximately 5.88 trillion miles. The distance that light itself, the fastest thing in the universe, travels in one complete year. Light is so swift that it could circle our entire planet 7.5 times in a single second. It crosses the distance from Earth to the Moon in just over 1 second, reaches the Sun in about 8 minutes, passes the orbit of Neptune in roughly 4 hours. Yet, even at this incomprehensible velocity, light requires more than 4 years to reach the nearest star beyond our Sun, a dim red dwarf called Proxima Centauri. That single journey from our solar system to its closest stellar neighbor spans a distance so vast that no human technology could traverse it in less than tens of thousands of years using our fastest spacecraft. And this distance, this 4 light year gap to the nearest star, is essentially nothing on the scale of the galaxy. It is a single step in a journey of billions of steps, a drop of water in an ocean that spans the world. The Milky Way's disk alone is 200,000 light years across, which means that light leaving one edge of the galaxy today will not reach the opposite edge until 200,000 years have passed. When that light finally arrives at its destination, everything about human civilization will have changed beyond recognition. Or perhaps human civilization will no longer exist at all, replaced by something else or by nothing. The light will complete its journey regardless, indifferent to the fates of the tiny creatures who once contemplated its path. Let us try to build some intuition for these scales through comparison, as through analogy, through the construction of mental models that might allow us to grasp, however imperfectly, what these distances actually mean. Imagine reducing the entire Milky Way so that our sun becomes a single grain of sand, roughly 2 millimeters across. At this scale, the Earth would be a microscopic speck, orbiting that grain at a distance of about 2 centimeters, far too small to see with the naked eye. The nearest star, Proxima Centauri, would be another grain of sand approximately 4 miles away. 4 miles to the nearest neighbor, with nothing but empty space between. Now consider the entire galaxy at this scale. The disk of the Milky Way, those 200,000 light years of stars and gas and dust, would span roughly the entire Earth, with grains of sand scattered every few miles on average, clustering more densely in some regions and spreading thin in others. The stellar halo would extend several times the Earth-Moon distance, with isolated ancient stars drifting in the darkness like dust motes in a vast cathedral. And the dark matter halo, that invisible envelope that contains most of the galaxy's mass, would reach almost to the moon itself. This is what we mean when we talk about the Milky Way, an entire planet covered in sand grains miles apart from each other, surrounded by a shell of darkness extending to the moon, and all of this representing just one galaxy among hundreds of billions in the observable universe. Perhaps time offers a better pathway to comprehension than space. Consider how long it would take to traverse these distances using various modes of travel. And if you could walk across the galaxy at a steady pace of 3 miles per hour, never stopping to rest or eat or sleep, it would take you approximately 400 trillion years to cross just the visible disk. The universe itself is only about 14 billion years old, so you would need to walk for roughly 30,000 times the current age of everything that exists. If you could drive across the galaxy at highway speeds, say 60 miles per hour, the journey would still take about 20 trillion years. If you could fly in a commercial airplane at 500 miles per hour, you would need about 2.4 trillion years. Even the fastest human-made object, the Parker Solar Probe, which reaches speeds of approximately 430,000 miles per hour when it swings close to the sun, would require roughly 125 billion years to cross the disk, more than 9 times the current age of the universe. These numbers should give you pause. They should make you feel something, some mixture of awe and vertigo, and perhaps a strange kind of peace. We are embedded in a structure so vast that no conceivable human technology could ever explore more than the tiniest fraction of it. The galaxy will forever remain mostly unknown to us, a mystery that we can contemplate but never fully penetrate. Even if we imagine technologies far beyond our current capabilities, the numbers remain staggering. Suppose we could somehow travel at the speed of light itself, violating no known physics, only because we are imagining rather than engineering. At light speed, crossing the Milky Way's disk would take 200,000 years. Crossing the stellar halo would take several 100,000 years more. Traversing the entire dark matter envelope could take up to 2 million years. These are not the timescales of human lives or human civilizations. These are geological timescales, evolutionary timescales, the kind of durations over which mountains rise and fall, and species appear and vanish. If our ancestors had launched a light-speed probe toward the far edge of the galaxy, when anatomically modern humans first appeared in Africa roughly 300,000 years ago, that probe would not have reached its destination yet. It would still have roughly 100,000 years of travel remaining, and this is just one galaxy. The observable universe contains hundreds of billions of galaxies, many of them larger than our own, scattered across distances that dwarf even the Milky Way's immense span. The nearest major galaxy, Andromeda, lies about 2.5 million light years away. The observable universe itself spans approximately 93 billion light years from one side to the other. And beyond the observable universe, beyond the horizon from which light has had time to reach us since the Big Bang, there may be vastly more space, extending perhaps infinitely in all directions. containing structures we will never see, never detect, never even confirm exist. The human mind recoils from such immensity, and perhaps that recoil is appropriate. Perhaps it is the only sane response to numbers that exceed all possible experience. Having established, however, inadequately, some sense of the galaxy's scale, let us now turn to our position within this vast structure, to the question of where exactly we find ourselves in the cosmic geography of the Milky Way. Our sun is one star among an estimated 200 to 400 billion stars in the galaxy, a number so large that if you tried to count them at a rate of 1 per second, it would take you somewhere between 6,000 and 12,000 years to complete the task, assuming you never pause to sleep or eat or do anything else. Among all these hundreds of billions of stars, our sun is remarkably ordinary. It is a yellow dwarf star, middle-aged at about 4.5 billion years old, average in size and temperature and luminosity. There is nothing special about it from a cosmic perspective, and nothing that would distinguish it from billions of similar stars scattered throughout the galaxy. And its position within the Milky Way is equally unremarkable. We orbit roughly 26 to 27,000 light years from the galactic center, placing us approximately halfway between the center and the outer edge of the visible disk. This is not a position of privilege or importance. We are not at the center of anything. We are in what might be called the galactic suburbs, a quiet neighborhood far from the bustling downtown of the galactic core. Our local region is called the Orion Arm, sometimes also known as the Orion Spur or the local arm. It is a minor spiral arm of the galaxy, a smaller structure nestled between two of the major arms, the Perseus arm to the outside and the Carina Sagittarius arm to the inside. If you could somehow hover above the galaxy and look down at its spiral structure, the Orion arm would appear as a relatively short segment of stellar concentration, less prominent than the great sweeping arms that define the galaxy's overall shape. We live in a cosmic side street rather than a main avenue, an astronomical backwater rather than a center of activity. But this modest position does not mean we are stationary. The sun, along with its planets and moons and asteroids and comets, is hurtling through space at tremendous velocity, orbiting the galactic center like a tiny boat caught in an enormous whirlpool. Our orbital speed is approximately 514,000 miles per hour, or about 230 kilometers per second. This is so fast that we cover the distance from Earth to the moon in roughly half an hour, at the distance from Earth to the sun in about a week. Yet even at this tremendous speed, the galaxy is so incomprehensibly large that completing a single orbit takes an almost inconceivable amount of time. One complete circuit around the galactic center requires approximately 225 to 250 million years. Astronomers sometimes call this period a galactic year or a cosmic year, and it provides yet another way to comprehend the timescales involved in galactic structure. In the entire history of our solar system, approximately 4.6 billion years since the sun and planets formed from a collapsing cloud of gas and dust, we have completed only about 18 to 20 orbits around the galaxy. The last time we were at this point in our galactic orbit, the dinosaurs were just beginning their rise to dominance on Earth. The next time we return to this spot, 250 million years from now, everything familiar about our world will have transformed beyond recognition. Our journey around the galaxy is not a simple circle, but a complex, three-dimensional path. The sun bobs up and down through the galactic disk as it orbits, like a horse on a carousel, crossing from one side of the disk to the other, roughly every 30 to 35 million years. We are currently located slightly above the midplane of the disk, about 65 to 100 light years north of the galactic equator. Over the next few million years, we will continue moving upward before reaching a maximum height and beginning to descend back through the disk. Some researchers have speculated that these oscillations might have biological significance, that passing through the denser regions of the galactic mid-plane might expose Earth to increased cosmic radiation or gravitational disturbances that could trigger mass extinction events. The evidence for this hypothesis remains inconclusive, but it illustrates how our position within the galaxy, seemingly abstract and distant from everyday concerns, might actually influence the history of life on our planet. Zooming out further, we find that our Milky Way is itself part of a larger cosmic structure called the local group. This is a collection of more than 80 galaxies bound together by mutual gravitational attraction, spanning a region approximately 10 million light years across. The local group is dominated by two large spiral galaxies, our Milky Way and the Andromeda galaxy, with everything else being smaller dwarf galaxies that orbit one or the other of these giants like satellites around planets. The Milky Way has at least 50 known satellite galaxies, including the large and small Magellanic Clouds visible from the southern hemisphere, and likely many more that remain undiscovered because they are too faint or too obscured by the disk of our galaxy to detect easily. These satellite galaxies range from relatively substantial objects containing billions of stars to tiny clumps of a few thousand stars that barely qualify as galaxies at all. Together with Andromeda and its own collection of satellites, they form a gravitationally bound family that will remain together even as the larger universe expands and carries other galaxy groups away from us. And the local group itself is located at the outskirts of a much larger structure called the Virgo supercluster, a collection of approximately 100 galaxy groups and clusters centered on the Virgo cluster about 50 million light years away. And the Virgo supercluster is just one small component of an even larger structure called Laniakea, a Hawaiian word meaning immense heaven, which contains roughly 100,000 galaxies spanning 500 million light years. At each level of this cosmic hierarchy, we find ourselves in an unremarkable position, neither at the center nor at the edge, just one more component in an endlessly nested series of structures that extend to the limits of observation and presumably far beyond. There is no special place in the universe, no cosmic downtown where everything important happens. There is only structure upon structure upon structure, galaxies within groups, within clusters, within superclusters, all of it embedded in the vast web of dark matter and dark energy that shapes the evolution of everything. To truly understand the Milky Way, we must journey inward toward its heart, toward the dense central regions where stars crowd together in numbers that dwarf the sparse stellar neighborhoods we inhabit. The galactic center lies approximately 26,000 light years from our solar system, hidden from direct optical observation by vast clouds of interstellar dust that absorb visible light and render the core invisible to ordinary telescopes. For centuries, astronomers could only guess what lay at the heart of the galaxy. It could only imagine what structures and phenomena might exist in that obscured region. But modern technology has given us new eyes, instruments that can see in infrared and radio wavelengths that pass through the dust as if it were not there. And what we have discovered at the galactic center is both magnificent and terrifying. The innermost region of the Milky Way is dominated by a dense bulge of old stars, a roughly spherical concentration extending about 10,000 light years from the center in all directions. These bulge stars are ancient, among the oldest in the galaxy, their red and orange hues indicating ages of 10 billion years or more. They formed in the earliest epochs of the Milky Way's existence, before the disk had fully settled into its current spiral shape. And they have witnessed the entire subsequent history of galactic evolution from their positions near the core. The stellar density in this region is extraordinary compared to our local neighborhood. Near the galactic center, stars are packed thousands of times more densely than they are near the sun. If Earth orbited a star in that region, our night sky would blaze with thousands of stars bright enough to cast shadows, a perpetual twilight that would make our familiar constellations seem lonely by comparison. But the true wonder of the galactic center lies deeper still, at the very heart of the bulge, where space and time themselves become distorted by the most extreme gravitational field in our galaxy. There, lurking in the darkness like a spider at the center of a cosmic web, sits a supermassive black hole designated Sagittarius A star. This object contains the mass of approximately 4 million suns, compressed into a region of space smaller than the orbit of Mercury around our sun. The black hole itself emits no light. By definition, nothing can escape from within its event horizon, but we can observe its presence through its effects on nearby matter. Stars in the galactic center orbit Sagittarius A star at tremendous velocities, some completing their orbits in just a few years, despite traveling paths that would take centuries at normal stellar speeds. One star, designated S2, has been tracked for decades as it whips around the black hole in an elongated orbit, approaching within about 17 light hours of the event horizon and reaching speeds of nearly 3% the speed of light at closest approach. These observations have allowed astronomers to calculate the black hole's mass with extraordinary precision and have confirmed predictions of Einstein's general relativity in the most extreme gravitational environment we can directly observe. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole, showing the supermassive black hole at the center of the galaxy M87. In 2022, they followed with an image of Sagittarius A star itself, revealing the glowing ring of superheated gas swirling around our own galactic black hole. That image, showing a dark shadow surrounded by a bright asymmetric ring, represented a triumph of human ingenuity, a picture of an object so strange that its existence challenges our intuitions about the nature of reality. And moving outward from the central bulge, we enter the most visually distinctive region of the Milky Way, the spiral arms that give our galaxy its classification as a barred spiral. These arms are not solid structures, like the arms of a starfish or the spokes of a wheel. They are density waves, regions where stars and gas temporarily crowd together before dispersing, like the compression waves that move through a traffic jam, even as individual cars eventually pass through and continue on their way. The Milky Way has 4 major spiral arms: the Perseus arm, the Norma arm, the Scutum Centaurus arm, and the Carina Sagittarius arm, along with several smaller spurs and branches, including our own Orion arm. These arms emanate from a central bar, an elongated structure of stars that stretches across the inner regions of the galaxy and from whose ends the spiral pattern emerges. The bar is estimated to be about 27,000 light years long, oriented at an angle of roughly 45 degrees to the line connecting our Sun to the galactic center. This bar is not unique to the Milky Way, but appears to be a common feature of spiral galaxies, perhaps forming through gravitational instabilities as galaxies evolve over billions of years. The spiral arms are where most of the galaxy's star formation occurs, where giant molecular clouds of hydrogen and helium collapse under their own gravity to birth new generations of stars. These young stars are hot and blue and luminous, and their brilliant light making the arms appear brighter than the spaces between them, even though the actual density of matter in the arms is only modestly higher than in the inter-arm regions. The arms are also where we find most of the galaxy's nebula, those glowing clouds of gas illuminated by the radiation of nearby stars. The stellar nurseries where new suns and new planetary systems come into being. The disk of the galaxy, containing both the spiral arms and the inter-arm regions, is remarkably thin compared to its width, like a cosmic DVD or a pizza stretched impossibly large. Near the Sun, the disk is approximately 1,000 light years thick, meaning that the ratio of diameter to thickness is about 200 to 1. If you scale the disk down to the size of an actual DVD, about 12 centimeters across, it would be proportionally thinner than a human hair. This extreme flatness results from the rotation of the galaxy, the same physical principle that causes a ball of pizza dough to flatten when a chef spins it in the air. The stars in the disk orbit the galactic center on roughly circular paths, their collective motion creating a centrifugal effect that pushes matter outward while gravity pulls it toward the mid-plane, resulting in a flattened, rotating structure. But the disk is not perfectly flat, especially at its outer edges. Observations have revealed that the Milky Way's disk is warped, bent upward on one side and downward on the other, like a vinyl record left too long in the sun. This warp is most pronounced in the outer regions of the galaxy, where the disk deviates from the midplane by thousands of light years. And the cause of this warping is thought to be gravitational interaction with the Magellanic Clouds, our largest satellite galaxies, whose combined mass is sufficient to tug on the outer disk and distort its shape over hundreds of millions of years. Recent observations have also revealed ripples in the disk, wave-like corrugations that may be the gravitational echoes of past collisions with smaller galaxies, frozen into the structure of the disk like ripples in a pond captured in a photograph. One of the most profound mysteries of the Milky Way, and indeed of all galaxies, is that most of its mass is invisible. When astronomers first began measuring how fast stars orbit within galaxies, they discovered something deeply puzzling. The stars at the outer edges of galactic disks were moving far too quickly, given the amount of visible matter present. According to the laws of gravity, as we understand them, those outer stars should have been moving more slowly, their orbits determined by the gravitational pull of all the stars and gas interior to their position. Instead, they were whipping around the galaxy at speeds that implied far more gravitational pull than the visible matter could possibly provide. Either our understanding of gravity was wrong at galactic scales, or there was matter present that we could not see. This mystery, first identified in the 1930s, but not widely recognized until the work of astronomer Vera Rubin in the 1970s, led to one of the most important concepts in modern astronomy, dark matter. A dark matter is the name we give to whatever substance provides the missing gravity, the invisible scaffolding that holds galaxies together and determines their structure. We call it dark because it does not emit light, does not absorb light, does not interact with light in any way. It is utterly invisible to all our telescopes, detectable only through the gravitational influence it exerts on visible matter. The evidence for dark matter in the Milky Way is overwhelming despite our inability to see it directly. The rotation curve of our galaxy, the graph showing how orbital velocity changes with distance from the center, remains flat far beyond where it should decline if only visible matter were present. The motions of satellite galaxies orbiting the Milky Way imply a total mass far exceeding what we can account for with stars and gas. And the shapes of stellar streams, those ribbons of stars torn from consumed dwarf galaxies, can only be explained if they are moving through a vast halo of invisible matter that shapes their trajectories. By combining all these lines of evidence, astronomers have constructed a picture of the Milky Way's dark matter distribution. The dark matter forms an enormous, roughly spherical halo that surrounds the visible galaxy, extending far beyond the stellar disk and the stellar halo into the depths of intergalactic space. This halo is not uniform, but contains substructure, clumps, and concentrations that correspond to smaller dark matter halos absorbed over cosmic time, the invisible counterparts of the dwarf galaxies that the Milky Way has consumed. The total mass of this dark matter halo is estimated at roughly 1 trillion solar masses, compared to about 200 billion solar masses for all the stars in the galaxy combined. This means that dark matter outweighs ordinary visible matter by a factor of roughly 5 to 1. The galaxy we see, the beautiful spiral we photograph and admire, is just the luminous tip of a vast dark iceberg, the small visible fraction of a much larger invisible structure. Despite decades of searching, we still do not know what dark matter actually is. The leading candidates are exotic particles that interact with ordinary matter only through gravity, particles that were produced in the early universe and have persisted ever since, filling the cosmos with an invisible sea of matter. These hypothetical particles have been given names like WIMPs, for weakly interacting massive particles, and axions. But despite extensive searches using underground detectors designed to catch the rare interaction between a dark matter particle and an ordinary atom, no definitive detection has been made. Other theories propose modifications to our understanding of gravity itself, suggesting that Newton's laws and Einstein's general relativity might need correction at galactic scales. But these modified gravity theories have struggled to explain all the observations as successfully as dark matter does. The nature of dark matter remains one of the greatest unsolved mysteries in physics, a puzzle that touches on fundamental questions about the composition of the universe and the laws that govern it. What we do know is that whatever dark matter is, it plays an essential role in the structure and evolution of the Milky Way. Without dark matter, or our galaxy would not have formed in the first place. In the early universe, dark matter began clumping together under its own gravity long before ordinary matter could do the same, creating gravitational wells into which ordinary matter eventually fell, condensing into the first stars and galaxies. Dark matter provided the seeds around which the visible cosmos grew, the invisible framework that made everything we see possible. In a very real sense, we owe our existence to a substance we have never detected and do not understand. The Milky Way is not a static structure frozen in time, but a dynamic, evolving entity that has been changing since its birth and will continue changing until its eventual dissolution in the unimaginably distant future. To understand our galaxy fully, we must consider not just what it is, but what it will become. The dramatic transformations that await in the cosmic timescales that stretch before us. The most significant event in the Milky Way's future is already underway. A slow motion collision that will fundamentally reshape our galactic home. The Andromeda galaxy, our nearest major neighbor, is currently hurtling toward us at approximately 250,000 miles per hour, closing the 2.5 million light-year gap between us at a rate that will bring the two galaxies together in roughly 4 to 5 billion years. This impending collision has been known for decades, but recent measurements from the Gaia spacecraft have refined our understanding of its trajectory and timing, confirming that a direct collision is essentially inevitable. When astronomers first recognized that Andromeda was approaching rather than receding, it came as something of a surprise, since the overall expansion of the universe carries most galaxies away from each other. But the Milky Way and Andromeda are close enough that their mutual gravitational attraction overcomes the cosmic expansion, drawing them inexorably together.
Our solar system will survive this merger, though its fate within the new combined galaxy is uncertain. Simulations suggest several possible outcomes depending on the precise details of the collision, which cannot be predicted with certainty given the timescales involved. In some scenarios, the solar system remains relatively close to its current position, simply becoming part of the merged galaxy's new structure. In other scenarios, gravitational interactions during the merger fling the solar system outward into the halo of the new galaxy, or even eject it entirely into intergalactic space, sending us wandering alone through the void between galaxies. None of these outcomes would directly threaten life on Earth, assuming any life still exists by then. The Sun itself will have exhausted its hydrogen fuel and expanded into a red giant star long before the Andromeda collision occurs, likely rendering Earth uninhabitable within the next 1 to 2 billion years. By the time the galaxies merge, our planet may already be a scorched cinder or may have been swallowed entirely by the expanding Sun. But if our descendants or their technological creations have spread to other star systems by then, they might witness the merger from a safe distance, watching as two spiral galaxies become one elliptical giant over the course of countless generations. Before the Andromeda collision, the Milky Way will likely absorb several of its smaller satellite galaxies, continuing a pattern of galactic cannibalism that has characterized its entire history. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are our two largest satellite galaxies, containing billions of stars between them. These galaxies are not in stable orbits around the Milky Way, but are slowly spiraling inward, losing orbital energy through a process called dynamical friction as they plow through the diffuse outer regions of our galaxy's dark matter halo. Current estimates suggest the large Magellanic Cloud will merge with the Milky Way in approximately 2 to 3 billion years, with the small Magellanic Cloud following shortly thereafter. These mergers will be relatively minor compared to the Andromeda collision, adding a few percent to the Milky Way's total mass rather than doubling it. But they will still produce observable effects, including distortions in the disk and bursts of star formation as gas from the satellite galaxies falls into our own. The stellar streams we observe today, those ribbons of stars tracing paths across the sky, are the remnants of previous such mergers, dwarf galaxies that fell into the Milky Way billions of years ago and were torn apart by tidal forces. Our galaxy has been growing by consuming smaller galaxies throughout its history, and it will continue this pattern until the Andromeda merger creates something new entirely. Looking further into the future, far beyond the Andromeda collision, we can trace the ultimate fate of our galaxy and all galaxies in the cosmos. The merged Milkomeda galaxy will itself eventually merge with the other members of the local group, the collection of more than 80 galaxies bound together by gravity. Over tens of billions of years, all these galaxies will coalesce into a single giant elliptical galaxy containing the combined stars of the entire group. But this merged local group galaxy will be increasingly isolated. The accelerating expansion of the universe, driven by the mysterious dark energy that comprises roughly 68% of all cosmic energy, is carrying other galaxy groups away from us at ever-increasing speeds. Galaxies beyond the local group are already receding faster than they were in the past, and this recession will continue to accelerate forever if dark energy behaves as current theories suggest. Eventually, other galaxies will be carried beyond our cosmic horizon, the distance from which light can ever reach us, and they will vanish from our observable universe entirely. The merged local group will find itself alone in an increasingly empty cosmos, the only structure visible in a sky that once blazed with billions of galaxies. The long-term fate of this isolated merged galaxy is determined by the fundamental physics of stars and the inexorable increase of entropy. Star formation will gradually cease as the available gas is consumed or heated beyond the point where it can collapse into new stars. The existing stars will age and die, their corpses taking various forms depending on their masses. Small stars like red dwarfs will burn for trillions of years, far longer than the current age of the universe, slowly consuming their hydrogen fuel until they fade into cooling white dwarfs. Larger stars will explode as supernovae or collapse into neutron stars and black holes. Over timescales that dwarf anything we have discussed so far, the galaxy will become increasingly populated by stellar remnants rather than living stars. White dwarfs will cool and dim, eventually becoming black dwarfs so cold they emit no detectable radiation. Neutron stars will spin down and grow quiet. Only black holes will remain as significant gravitational players, slowly growing as they occasionally consume matter that wanders too close. On timescales of 10 to the 20th power years and beyond, even the structure of the galaxy itself will dissolve. Gravitational interactions between stellar remnants will occasionally give one object enough velocity to escape the galaxy entirely while removing energy from others, causing them to sink toward the center. Over truly cosmic timescales, the merged galaxy will evaporate, its components scattered into the void or consumed by the central black hole. Eventually, nothing will remain but black holes drifting through infinite darkness, and even these will ultimately evaporate through Hawking radiation on timescales of 10 to the 67th power years or more. The Milky Way, once a blazing spiral of hundreds of billions of stars, will vanish entirely, leaving no trace that it ever existed. Understanding why measuring the Milky Way matters requires stepping back from the technical details and considering what this knowledge means for humanity, for science, and for our understanding of our place in existence. On a practical scientific level, knowing the true size of our galaxy affects almost every aspect of astronomical research. The Milky Way is our primary laboratory for understanding how galaxies work. We can study individual stars, nebulae, and stellar populations in our galaxy with a level of detail impossible for more distant systems, where everything blurs together into unresolved points of light. But to properly interpret these observations, we must know where things are located within the galactic structure, how far apart different components are, how the galaxy's gravity shapes the motions of stars and gas. Every measurement of the Milky Way's size ripples outward into other areas of astronomy, affecting our estimates of galactic mass, our models of dark matter distribution, our understanding of stellar evolution and chemical enrichment, our searches for potentially habitable worlds around other stars. When we revised the size of the Milky Way's disk upward from 100,000 to nearly 200,000 light-years, we were not just changing one number in an encyclopedia. We were adjusting a fundamental parameter that influences countless other calculations and conclusions throughout astronomical science. Beyond the practical scientific implications, there is something profound about knowing the true dimensions of our cosmic home. Humans have always sought to understand their place in existence, to answer questions about where we are and what surrounds us. The earliest humans looked up at the stars and wondered what they were, where they ended, how far they extended. Every subsequent generation has pushed the boundaries of knowledge outward, discovering that the Earth was round, that the Sun was a star, that the Milky Way was a galaxy, that our galaxy was one among billions. Each discovery has simultaneously expanded our understanding and deepened our sense of cosmic humility. We are not at the center of the universe, not at the center of the galaxy, not even in a particularly special location within our galactic neighborhood. We are peripheral in almost every measurable sense, tucked away in the suburbs of an ordinary galaxy, in an ordinary galaxy group, in an ordinary supercluster, in one small corner of an inconceivably vast cosmos. And yet this very peripherality makes our achievements all the more remarkable. From this unremarkable location, using only the light that reaches our instruments and the mathematics we have developed to interpret it, we have managed to measure the dimensions of a structure 200,000 light-years across, and deduce the existence of invisible matter that outweighs everything we can see. We have traced the history of our galaxy back billions of years and projected its future trillions of years ahead. We have connected ourselves to the cosmic web that spans the observable universe and glimpsed structures beyond anything our ancestors could have imagined. There is something deeply moving about this achievement, something that speaks to the best aspects of human nature. We are curious creatures, driven to understand even when understanding serves no immediate practical purpose. No one's daily life will change because we now know the Milky Way is larger than we previously thought. No technology will be built, no disease cured, no hunger alleviated because we have mapped the positions of 2 billion stars. And yet this knowledge enriches us, expands our sense of the possible, connects us to something larger than ourselves and our immediate concerns. When you look up at the night sky and see that pale band of light stretching overhead, you are looking at your home. You are seeing the combined glow of hundreds of billions of stars, the visible portion of a structure that extends far beyond what your eyes can detect. A structure that has existed for more than 13 billion years and will continue existing in some form for trillions of years to come. You are part of this structure made from its atoms, participating in its ongoing evolution. A tiny but genuine component of something magnificent beyond description. The measurement of the Milky Way is ultimately the measurement of ourselves, the quantification of our context, the determination of where and what we are in the grand scheme of cosmic existence. To know the size of our galaxy is to know something essential about our place in the universe, to have answered, however partially, one of the oldest and deepest questions humans have ever asked. How big is the world? Larger than we ever dreamed, more magnificent than we ever imagined, and still somehow, against all odds, our home. As we approach the conclusion of our journey through the Milky Way, it becomes necessary to reflect on the extraordinary scientific odyssey that brought us from ancient wonder to precise measurement, from philosophical speculation to empirical knowledge. The story of how humanity came to understand the true size of our galaxy is not merely a chronicle of technical achievements, but a testament to something profound about the human spirit. A demonstration that curiosity combined with persistence can penetrate mysteries that once seemed utterly impenetrable. Consider for a moment what our ancestors faced when they first began asking questions about that pale band of light crossing the night sky. They had no telescopes, no understanding of what stars actually were, no conception of the vast distances involved, no mathematics adequate to describe cosmic structures. They had only their eyes and their wondering minds, their capacity to look upward and ask what and how and why. From those humble beginnings, across thousands of years of incremental progress punctuated by revolutionary insights, we have arrived at a point where we can state with confidence that the Milky Way's disk spans approximately 200,000 light-years, that its stellar halo extends hundreds of thousands of light-years further, that its dark matter envelope reaches perhaps 1,000,000 light-years from the center. These numbers represent the accumulated effort of countless individuals across dozens of generations, each building on the work of those who came before, each contributing some small piece to a puzzle that no single person could ever complete alone. The progression from Democritus speculating about distant stars to Gaia mapping 2 billion of them spans nearly 2.5 millennia, and every step along the way required courage as well as intelligence. Galileo faced persecution for challenging the established view of the cosmos. Henrietta Leavitt worked in obscurity, denied the recognition she deserved because of her gender, yet made a discovery that revolutionized our ability to measure the universe. Harlow Shapley overturned the comfortable assumption that we occupied a central position in the galaxy, displacing humanity to the cosmic suburbs. Edwin Hubble shattered the boundaries of the known universe, revealing that our galaxy was just one island among billions in an ocean of space vaster than anyone had suspected. Vera Rubin's observations of galactic rotation curves pointed toward the existence of dark matter, revealing that most of the universe is invisible to us, that we had been seeing only a small fraction of reality. Each of these breakthroughs required not just intellectual insight, but a willingness to follow the evidence wherever it led, even when it led to conclusions that challenged cherished beliefs or comfortable assumptions. Science progresses not by confirming what we want to believe, but by testing what we think we know against the unforgiving standard of observation and measurement. And the history of understanding the Milky Way is a history of being repeatedly surprised by a universe far stranger and larger than we had imagined. The tools that made this understanding possible represent another dimension of human achievement, a parallel story of technological innovation driven by the desire to see further and more clearly. The progression from Galileo's simple refracting telescope to the sophisticated instruments we deploy today spans 4 centuries of continuous improvement, each generation of technology enabling observations that were impossible for previous generations. Consider what Gaia represents in this progression. The spacecraft measures stellar positions with an accuracy of about 20 microarcseconds, which corresponds to the angular size of a human hair viewed from a distance of 1,000 kilometers. This level of precision would have seemed magical to astronomers just a few decades ago, and would have been literally inconceivable to astronomers of previous centuries. The techniques involved require not just precise optics and sensitive detectors, but sophisticated mathematical methods to account for the countless factors that can introduce errors. From the subtle distortions of the spacecraft's structure as it moves between sunlight and shadow to the bending of starlight as it passes through the gravitational field of the sun. Every Gaia measurement is a triumph of engineering and mathematics, a successful navigation through a maze of potential errors to arrive at a number that can be trusted. And Gaia is just one instrument among many, one node in a global network of telescopes and observatories that together provide humanity with unprecedented eyes on the cosmos. The discovery that the Milky Way is nearly twice as large as we previously believed forces us to update not just our scientific models, but our mental images of the universe we inhabit. When you visualize our galaxy, you might picture the classic spiral scene in artists' renditions, a pinwheel of luminous arms surrounding a bright central bulge. This image is not wrong, but it is incomplete. It shows only the visible portion of a much larger structure, like a photograph of an iceberg that captures only the tip above the waterline, while the vast bulk remains hidden below. The true Milky Way extends far beyond that familiar spiral, reaching outward through the diffuse stellar halo where ancient stars drift in isolation, continuing further still through the invisible dark matter envelope that contains most of the galaxy's mass. When you look up at the night sky, you are not seeing the edge of the galaxy in any direction. The stars you can observe with your naked eye are all relatively nearby, the closest neighbors in a collection of hundreds of billions, and beyond them stretch distances that light itself takes hundreds of thousands of years to cross. The galaxy is not just above you, forming that pale band across the sky. It is all around you, extending in every direction, a structure so large that you are embedded within it like a single cell within a vast organism. This updated picture of the Milky Way also changes how we think about the possibilities for life beyond Earth. The search for extraterrestrial intelligence has often focused on the idea that our galaxy might host numerous technological civilizations, that among hundreds of billions of stars, there might be countless worlds where life has arisen and evolved toward intelligence and technology. The discovery that our galaxy is larger than previously thought means there are more stars than we had counted, more potentially habitable worlds, more opportunities for the emergence of life. But it also means the distances between potential civilizations are even more vast than we had imagined, making communication or travel between them even more challenging. If another civilization exists on the far side of the galactic disk, any message we sent them would take 200,000 years to arrive, and their response would take another 200,000 years to reach us. Conversations across such timescales are effectively impossible for mortal beings. The vastness of the galaxy that makes the existence of other life seem probable is the same vastness that makes contact with that life seem nearly impossible. We may share our galaxy with countless other intelligences, and yet remain forever isolated from them, separated by distances that no technology can meaningfully bridge. The implications of the Milky Way's true size extend beyond questions of extraterrestrial life to fundamental questions about the nature of reality and our place within it. Modern physics tells us that the universe operates according to consistent laws, that the same equations describe phenomena here on Earth and in the most distant observable galaxies. Yet the scales involved in cosmic structures strain our ability to apply those laws intuitively. We understand gravity, but we struggle to truly comprehend what gravity means when it holds together a structure spanning hundreds of thousands of light years. We understand that light travels at a finite speed, but we struggle to grasp what it means that light from the far edge of our own galaxy will not reach us during any human lifetime. That the galaxy is so large it contains regions we can never communicate with even in principle during any realistic time frame. These are not failures of physics but failures of intuition, reminders that human minds evolved to navigate environments measured in meters and kilometers, days and years, not light years and cosmic ages. The universe does not conform to the expectations built into our brains by millions of years of evolution, in a small corner of one planet orbiting one ordinary star. Understanding it requires us to transcend those expectations, to build mathematical and conceptual frameworks that extend our native capabilities into domains where they would otherwise be helpless. There is a particular kind of wisdom that emerges from contemplating structures as vast as the Milky Way, a perspective that is simultaneously humbling and inspiring. On one hand, the scale of the galaxy makes human concerns seem vanishingly small. Our entire recorded history spans perhaps 5,000 years, less than 1/50,000th of the time required for light to cross the galactic disk. The total extent of human exploration, from the first migration out of Africa to the astronauts who walked on the moon, covers a distance that is essentially zero on galactic scales. Everything humanity has ever built, every monument and city and civilization, occupies a single planet that could be lost in the galaxy like a grain of sand lost in a desert. From the perspective of the Milky Way, humanity is invisible, our achievements imperceptible, our struggles and triumphs playing out on a stage too small to register. And yet, from another perspective, the very fact that we can comprehend the galaxy, can measure its dimensions and trace its structure and understand its composition, elevates us to a remarkable position in the cosmic order. We are the universe becoming aware of itself, the arrangement of matter that has developed the capacity to contemplate its own context. The atoms in our bodies were forged in stars that lived and died billions of years ago, scattered across the galaxy before coming together to form our solar system, and now those atoms have organized themselves into structures capable of understanding their own origins. We are not merely in the universe. We are the universe experiencing itself, a tiny eddy of consciousness in a vast ocean of mostly unconscious matter and energy. This perspective can serve as a source of both humility and motivation. Humility because we recognize how small we are, how limited our position, how vast the regions we will never explore and never understand. Motivation because we recognize that understanding itself is an achievement of cosmic significance, that every piece of knowledge we gain represents a triumph of mind over the darkness of ignorance. The measurement of the Milky Way is not just a scientific accomplishment, but a philosophical one, a demonstration that human beings can reach beyond their immediate circumstances to grasp truths about structures far larger than themselves. When we look up at the night sky and see that pale band of starlight, we are not just passive observers of something beyond our comprehension. We are active participants in the ongoing project of cosmic understanding, contributors to a tradition of inquiry that stretches back to the first humans who wondered about the lights in the darkness above them. The galaxy does not care about us, cannot care about us, has no awareness that we exist. But we care about it, and that caring, that curiosity, that drive to understand, is itself something remarkable in a universe that is mostly cold and dark and empty. We bring meaning to the cosmos by the very act of trying to understand it. And in that act, we achieve something that transcends our small size and brief existence. The scientific implications of understanding the Milky Way's true size ripple outward into virtually every branch of astronomy and astrophysics, creating connections and consequences that might not be immediately obvious, but that fundamentally shape our understanding of the cosmos. When we revised our estimate of the galaxy's diameter from 100,000 to nearly 200,000 light-years, we were not simply updating a single entry in a cosmic encyclopedia. We were adjusting a foundational parameter that influences calculations throughout the astronomical sciences, a change that propagates through equations and models like ripples spreading across a pond. Consider the question of galactic mass, one of the most important properties for understanding how galaxies form, evolve, and interact with their environments. The mass of a galaxy determines its gravitational influence, which in turn determines the motions of stars within it, the orbits of satellite galaxies around it, and the fate of gas and dust that falls into it. Estimating galactic mass requires knowing the size of the system, because mass is calculated from the velocities of objects at known distances from the center. If we thought the Milky Way extended 100,000 light-years, and then discovered it actually extends 200,000 light-years, we must reconsider how much mass is required to keep those outer stars gravitationally bound. The larger galaxy requires more mass to explain the observed motions, and since the visible matter has not increased, that additional mass must come from dark matter. Our understanding of the Milky Way's dark matter content is thus directly linked to our understanding of its physical extent, and revisions in one area necessitate revisions in the other. The implications extend to our understanding of galactic structure and dynamics. The spiral arms of the Milky Way are not static features, but dynamic phenomena, density waves that propagate through the disk over hundreds of millions of years. The behavior of these waves depends on the properties of the disk they propagate through, including its size, mass distribution, and rotation curve. A larger disk means the waves have farther to travel, interact with different stellar populations, and potentially behave differently than they would in a smaller system. Similarly, the bar at the center of the galaxy, that elongated structure from which the spiral arms emerge interacts with the surrounding disk in ways that depend on the disk's properties. Understanding the evolution of galactic structure requires accurate knowledge of galactic dimensions, and as those dimensions are revised, our structural models must be revised accordingly. The same is true for our understanding of chemical evolution. The gradual enrichment of the galaxy with heavy elements produced in stellar interiors and distributed by supernova explosions. The rate at which heavy elements spread through the galaxy depends on the distances involved and the mixing processes that operate over those distances. A larger galaxy means longer mixing timescales, different enrichment patterns, and potentially different conclusions about the ages and origins of stellar populations in different regions. Beyond these technical scientific implications, the revised size of the Milky Way affects our search for life beyond Earth in ways both encouraging and sobering. The Drake equation, that famous attempt to estimate the number of technological civilizations in our galaxy, includes a factor for the number of stars in the Milky Way. If the galaxy is larger than we thought, it likely contains more stars than we had counted, which increases the potential number of habitable worlds and the potential number of sites where life might have arisen. This is encouraging for those who hope we are not alone in the universe, who dream of someday detecting signals from another civilization or discovering evidence of life on distant worlds. But the larger galaxy also means greater distances between potential civilizations, longer communication times, and reduced chances of meaningful contact even if other intelligences exist. The nearest technological civilization might be tens of thousands of light years away rather than hundreds or thousands, placing them beyond any realistic possibility of two-way communication during the lifetime of either civilization. The galaxy might be teeming with life, and yet effectively empty from our perspective, each island of intelligence isolated by gulfs of space too vast to bridge. This is a sobering thought for those who imagine humanity someday joining a galactic community of civilizations, and it underscores the importance of cherishing and preserving the one example of life we know for certain exists.